Give some people time to trickle in, and we'll get started. Alrighty, we'll go ahead and get started. Hey everybody, my name is Jordan Manning. I'm part of the data science team at Abe.ai. It's a local company here in Orlando. We provide conversational banking solutions to financial institutions. I've been with the company for quite a while, and all the tech related to the conversational banking is and was grown in-house, developed in-house. Today, I'd like to present on a topic called virtual assistants, understanding the understanding. So essentially, after this presentation, I'd like you to be able to leave being able to better answer a few questions. What are virtual assistants? In this case, we're talking about the AI virtual assistants, not the virtual assistant as an occupation. Where are they used? Which industries, which channels, and most importantly, the bulk of this conversation will be around how do they understand natural requests, human language. Natural and human are kind of interchangeable, so if you hear natural language and human language, they mean the same. If you have questions, feel free to fire them off throughout the chat. What I'll probably end up doing is going through the presentation and then reviewing the chat at the end. I'll allot some time for question answering then. Or if you want, you can hold off until the end to ask your questions as well. Have some disclaimers here. The idea behind this talk is it's not necessarily to go deep into each technology, uncover the algorithm, write it from scratch. That's not the purpose of this presentation. It's more so to give you a glimpse or an intuition on how things work, with the hope that if you have more questions, you can either ask me directly, or there's tons of information on the internet. You can research further there. But because of time, we only have an hour here, and there's quite a few technologies involved in virtual assistants. It's best that we touch the surface and then leave any further investigation for you to do independently, or shoot me a message. There will be some oversimplification in some of the pictures or illustrations. So what is being illustrated isn't necessarily how it works 100% behind the scenes, but the oversimplification is necessary in order to communicate the idea in a more convenient fashion. And the ideas that we'll go through, I think they're comprehensive, but not exhaustive. So they don't cover, this isn't going to cover every single technology that exists out there. But I think we hit some of the bigger ones. But there's always something out there that won't be uncovered. So this will be comprehensive, but not necessarily exhaustive in that sense. So the most important question that we need to answer first, or be able to answer, is what is a virtual assistant? And long story short, it's basically software that can perform an action or answer a question, right? So if I give it a command to perform an action, if I ask it a question, it can answer it. Some super common examples that I use personally are asking about the weather. So how's the weather? So that's a question. And then I've got a smart light set up in my house. So asking it to, or commanding it to turn the lights off. So these are some of the actions or examples of actions and questions that virtual assistants are commonly used for. But in a nutshell, it's software that can answer a question and perform an action after being given a command. So where are virtual assistants used or seen? I think most people nowadays are pretty familiar with these, at least one of these. You've got the Google Assistant on the far left. You've got Siri in the middle, and then you've got Amazon Alexa on the right. Now, these are particular styles of virtual assistants. They take a general approach. They cast a wide net. So they're trying to answer everything from how's the weather to how old is Michael Jordan. Very general approach, which can be very difficult. They're not super specialized. But because of that, because of their ability to generalize, these are the most used virtual assistants. There's a lot of debates on which is best. There's pros and cons to each of these. Some do things better than others. I personally like the Google Assistant ecosystem. That's what I use for all of my smart home devices. But I've also had good experiences on Siri and Amazon Alexa. But these cast a wide net. They're not trying to specialize. Now, you also have assistants that do a specific task. The image on the far left portrays TripAdvisor, somebody asking about sushi restaurant. Where's a restaurant at? Sushi restaurant, and it's able to answer. In the middle is an example, actually from our product, and the user's asking about student loan refinance rates. So, a loan query, and it did that flow after that question. And on the far right, flowers, 1-800-Flowers. So there's a virtual assistant for executing flower transactions as well. So these applications, they're not trying to do what Google Assistant, Siri, and Amazon Alexa are doing with the casting a wide net. They're trying to do something more specific, more niche. So where exactly are these virtual assistants found? Which channels? So we realize, okay, you can ask certain virtual assistants basically any question. There are certain virtual assistants that are focused more on a specific topic. But where do they live? They basically live in all channels at this point. You saw before, there's the Google Assistant, just in the Google channel, Amazon, SMS, which is texting, Facebook Messenger. Some of these virtual assistants are embedded in web and mobile. So if you go online on a website, you'll get a pop-up and you can talk to a virtual assistant, and even IVR as well. So you make a phone call. I know many folks don't have the best experience with calling in and getting to a robot essentially, but these virtual assistants that are becoming more intelligent are actually much more helpful. They can understand. It's not just press 1, press 2. It's more natural. So now that we know what a virtual assistant is, how it's used, where they live, we can start talking about, well, how does a virtual assistant understand? And in order to do that, we need to have an understanding of what natural language understanding is. And shortened, it's NLU. And NLU is essentially a type of artificial intelligence that focuses on understanding human language or understanding natural language. So it's natural language understanding is very explicit. It feels redundant in the definition, but that's what it is. It's trying to understand human language. It's the AI, the branch of AI, category of AI that focuses on understanding human language. And so, well, what does that mean? What does it mean to understand human language? There's quite a few different ways you can look at that. The way that we're going to be looking at it is from the perspective of a virtual assistant. So what are the important parts of human language in order for me to understand what the user is saying, or the end user that's messaging me or speaking to me? And there's really 3 big components of natural language understanding from the perspective of a virtual assistant. You have intent classification. Basically, that's what's being asked or commanded. Like, what's the goal? What is the user trying to do? Earlier, I had some examples about weather, about turning the lights off. Like, those are the things that I want to do. Those are my intents. I want that to happen. That's the intent. There's also entity recognition. And what this is within that request, are there any other pieces of information that could be useful, right? So if I say, turn off the lights, that's pretty straightforward. But if I say turn off the kitchen lights, there's that extra piece of information, kitchen, that can further improve the experience so the virtual assistant knows to turn off specifically the kitchen lights. That would be considered an entity, the kitchen. And last but not least, dialogue. And a dialogue is essentially saying, okay, once I do something, what's the next step? What do I do next? I could, end the conversation or end the interaction, or I need to do some more things in order to fulfill the whole interaction. So you've got intent classification, what does the user want? Entity recognition, are there any specific details in what the user wants? And dialogue, which is, okay, once that's established, what do I need to do next? Are there any things that I need to do next in this, in this chain? So before we start talking about the different approaches to intent classification, entity recognition, and dialogue, I'd like to take a little bit of time to differentiate two approaches to those specific pieces of tech. So what you have here is one approach which is considered to be rule-based, and this is more classical, this is more traditional. Basically what this is the developer or whoever's creating this virtual agent is creating the logic. They're handcrafting the logic. They're explicitly defining what needs to be done when. And I like to think of this as developer-driven because it's somebody actually, decide on the rules using, they're making the decisions on what needs to happen. So I've included this photo of a, if you're not too familiar with code, it's basically showing like how complicated something can get with the logic as you introduce more and more conditions or scenarios. So it basically just becomes nested and it gets deeper and deeper and deeper into the logic, and it can be kind of difficult to understand. So rule-based is developer-driven. It's explicitly defined. Somebody is essentially like handcrafting or like making those decisions on what happens when. On the flip side, the other approach is machine learning, which can be shortened by ML. Now, instead of somebody explicitly defining these rules for the natural language understanding, and instead of it being developer-driven, it's actually data-driven, and the rules aren't explicitly defined. In this situation, this approach, instead of writing quite a few if-else statements or very customized logic, you feed a model a bunch of data, and the data implicitly, inherently, kind of makes its mind up and its rules, for lack of better expression. And when it makes a prediction, that's the decision that it's come up with. So rule-based, handcrafted, somebody's figured out the logic, typed it out, maybe some if and else statements. Machine learning is data-driven. All of that logic is kind of embedded in the data, and the model processes the data and implicitly comes up with those same types of rules that may have been rule-based, but maybe even more complex, maybe even things that are harder for humans to conceptualize. So just to recap, rule-based, developer-driven, and machine learning is data-driven. And what we'll end up doing is we're going to go through different approaches for intent classification, entity recognition, and dialogue, and how those approaches within that, how you may use a rule-based approach or a machine learning approach. So just to recap on intent classification, what does the user want? What do they want to happen, or what information do they want? Typically, when you refer to a user's message, it's considered an utterance, and what they want to happen is considered the intent. So what is the intent of the user given their utterance? So intent classification is just a fancy way of saying text classification. It's intent classification when you're speaking about virtual assistants. So in this example, what you can see is on the left, you've got a list of utterances. On the right, you have the corresponding intent. So how's the weather? Is it going to rain? Those would both be weather requests. Turn off the lights would be a light request, and order some food would be a food request. So I took these images here, and these actually are from a previous slide, just to better demonstrate what the intent would be in these examples. So for the image on the left, what are your current student loan refinance rates? The intent is to get information on student loan refinance rates. Simple as that. And you can see that the virtual assistant was able to understand it and then took the user to the next step. On the right, TripAdvisor, find sushi restaurant near me. So this is more of a command, and you can see that the assistant there was able to send information regarding sushi restaurants or restaurants. So how is this done? And what we'll do is we'll start off with rule-based, and then we'll move into machine learning approaches, and we're going to do that for intent classification, entity recognition, and dialogue. So if you think about it, one of the more intuitive, understandable ways and simple ways to do this would be to just do a simple lookup. And what this means is you have a list of utterances that you may expect to be said. And when the user says something, you check to see if that utterance that the user said is in your list. If it is, cool, understand what they said. If it isn't, then you may fall back to something like, hey, I don't know what you're talking about, some sort of unknown or uncategorized intent. So in this example, if you can just imagine if the list of expected utterances that you've defined is just two, and it's transfer money and send money to my account. And this is obviously for a transfer request. That's the idea. Now, if the user says transfer money, there's a match. So you can understand that and you can respond accordingly. Where this falls short is anything outside of that list isn't going to be caught. So if a user says transfer money, please, no match. So what you'll end up doing is returning, hey, not sure what you're talking about. Maybe try to rephrase. So you can see that even though it's simple, it's pretty easy to overwhelm. It's very difficult to account for all the different variations in something that a user would say or users would say. So this particular example just goes to show, like, you have to, if you're going to take this approach, you have to have a huge list, which is pretty unsustainable, unmanageable. But it is super simple and it's quick because it's lookup. Okay, moving on. So after looking at the lookup, checking out the lookup, maybe that's not the best approach. There's another concept called fuzzy. Now, first step is the same. You create a list of utterances that you would expect. The difference here is what you want to do is you'll want to find and pick out an algorithm that essentially compares two pieces of text and tells you how similar those pieces of text are based on the characters in the text. So it's going to give you a score, how similar this piece of text to this piece. After you pick that algorithm, you'll run that. You'll run that through. You'll have your user utterance come in, and you'll compare the utterance to what you have stored as the expected utterances, and see if there's a good match. So same examples as before. The list that the assistant knows is transfer money, send money to my account. And let's assume that the user says transfer money. This will match one of the items in the list at 100% because it's the same exact text. That's the score is 100. If somebody says transfer money, please, now this is where the lookup failed because it's not an exact match. This matches transfer money with a score of 88. So you're probably thinking, well, is that good enough? 88 is relatively high for a match. It all depends on your use case. If you require, if you don't want to have so many false positives, if you're okay with false negatives, you may want to increase that threshold, the score threshold, up to something higher than 90. But in this case, I would say it's a good match, and that would trigger the transfer request from the assistant. The third example is a little bit different. It's the first example just switched in the order. So money transfer, it matches transfer money at 56. And this is not ideal. It's the same meaning, money transfer, transfer money. The issue is because of the algorithm of fuzzy, and we're not doing any sorting or anything here. It's just, one-to-one, no processing. Money transfer and transfer money, if you look at them from end to end, it's not that close of a match character-wise, so it doesn't have a high score. So in this case, if somebody said money transfer and you're using a fuzzy approach, 56 is a low score. You probably would respond with, hey, I'm not sure what you're talking about. You want to have a higher score than that. So we saw how lookup, it was simple, easy to implement, but it had the issue of, if there's any utterance that's not exactly matching, it won't get it. Fuzzy can handle some variations that aren't exact, but big variations where it's the orders being swapped or many words in between, the score will be reduced and it won't hit that threshold, and it won't. The assistant will not understand. So another rule-based approach would be keyword. Essentially, what this is it's defining a list of keywords that you want to associate with an intent, and then you check if any of those keywords are found in that user utterance coming in. This example, we're still sticking with the transfer money example. So maybe you think, okay, well, if anybody says transfer, send, or move, I want that to be identified as a transfer request. So we'll go through the same examples before. Transfer money contains transfer. Cool, we're good there. Transfer money, please, also contains transfer. Great. Money transfer. So this is where fuzzy failed, essentially, did not understand. It contains transfer. So in this case, it's a good match. We can respond appropriately, so it knocks that one off. But if somebody says transfer human or transfer to human, even though the utterance contains the word transfer, it's not the right intent. The assistant will respond with a transfer money response, but in reality, the user wants to talk to a human. So this is where, even though the keywords search can help with some of the issues that Lookup has or Fuzzy would have, it can get quite complicated, because what you'll end up doing is, creating this crazy branch logic that, hey, if it contains transfer but not the word human, and you can just imagine how that grows. It gets so complicated, it's almost unreadable at that point with all the different variation logic. So those were 3 examples of rule-based approaches for intent classification. Now we'll move on to machine learning-based approaches. One of the more common ML approaches for intent classification, or even text classification in general, it's called bag of words. Essentially what this means is you give a model a list of utterances. It trains on those utterances. By train, all I mean is it processes those utterances. Now, those utterances need to be in a certain form for the assistant, for the model to understand what it is. It can't just go in as plain text. It needs to be converted things. So what ends up happening is that list of utterances provided to the model, there's a vocabulary that gets formed from that list. So it'll pick out all the words that occur in that list of, in those lists, or in the list of utterances. And use that vocabulary to map or transform the utterances. So in this example, just to keep it simple, the idea is that the assistant or the model only knows about the words transfer, send, money, please. So that's its vocab, its range of vocab. And then incoming utterances, transfer money, will be transformed to basically 1010. So what that 1010 means, if you look at the transfer, send, money, please, it's corresponding to those words. So which of the vocab exists in that utterance? So transfer is the first one. Okay, that's cool. That's a 1. Send is not in transfer money. Money is, that's a 1. Please is not in transfer money. And it's the same thing for please send money. So all this is doing is taking the input to the model, but it's transforming it into a more machine readable way so the model can process it and make a prediction. So essentially what happens is all that training data is provided to the model. It looks at all of the utterances that have been transformed. When an incoming utterance comes, like when there's an incoming utterance, that utterance is transformed as well and compared to all the other already trained utterances. And based on that comparison, the model is kind of looking for what's considered like an overlap, sort of. Based on that comparison, the model will make a prediction on whether or not it's similar to all the utterances in that intent. Now, I'll show an example after this here. So what this is showing is essentially the vocabulary of the model in the top, transfer and money, and then the utterance that's coming in, and what the model will decide to do based on those two, based on that combination. So if you can anticipate, if the only vocabulary that's known is transfer money, the utterance coming in, transfer money, would be 1 and 1. The model understands those two words coming in. It's seen them before. So the result will be the transfer request. Transfer money, please, same idea here. Transfer and money are both known in the vocab. Please is outside of the vocab. It's ignored. So the result is transfer. Money transfer, which Fuzzy had difficulty with. Same idea here. Money and transfer are both known. Transfer request. Now this is what the difference between the bag of words approach and the keyword lookup approach. The transfer to human threw off the keyword lookup because of the transfer. But in this case, if you look at transfer to human, the only word that's known is transfer. That's not, and this is just an assumption. I'm not sure how this would actually play out if a model is trained, but let's assume that that's not enough information for the model to be confident that that's a transfer request. So it gives the unknown response. Hey, I don't know what you're talking about. So in this case, the keyword lookup, the problem that it had is somewhat resolved by the bag of words approach, because it's not only taking in the transfer, but also the lack of the word money. And the last one is transfer funds. So the difference here is we want transfer funds to actually trigger the transfer request intent. But the word transfer is known, so it gets the 1. There's no money. Funds is not known by the model. So even though funds and money are similar, because the bag of words is only looking at the existence of the word, not anything about the word itself, it gets a 1 and 0, and the assistant will end up categorizing that or classifying that as unknown, which can be problematic. You'd want that to be caught, but due to the nature of the bag of words approach, and it's checking for the existence of the words as opposed to the meaning of the word, it classifies it as unknown. So this is one of the shortcomings of bag of words, is the focus on just the word and not anything else about the word. This is another approach, a little bit more sophisticated ML approach to intent classification. So what ends up happening is, it's something that I mentioned before in the previous, in the bag of words. The bag of words isn't looking at anything to do with the word, it's just the existence of the word. So the idea came about, hey, can we somehow create a numeric representation of a word that can be used to compare different words to see how similar they are in terms of like use. So that's what some folks did, is they essentially they use these giant data sets, Wikipedia, to analyze different words and their relations and how similar they were to each other. And the similarity isn't necessarily they have to be synonyms, but if they're used in similar ways, that's a similarity as well. So words that are used in similar ways, they'll end up having these similar numeric representations. This is what the numeric representation looks like. It's a vector. For this particular, there's different sets of embeddings. This particular set of embeddings has 300 different numbers associated with it. It's a vector dimension 300. And on the left is the numeric representation for the word digital. And on the right is the numeric representation for the word Orlando. So instead of using just the word digital and Orlando as like 0 and 1, like it exists or doesn't exist, we can also embed that information on, this is essentially, what does the word mean from the assistant's point of view. This will provide a little bit more intuition on that. So when you're looking at the embeddings, since they're vectors, you can compare them and calculate the similarity between the two different vectors. Some technical details here. These calculations below were done using cosine similarity on a scale of 0 to 1. So what this is showing is the similarity between dog and cat from the assistant's point of view, using those numeric representations, is 0.8, which is pretty high. Now, dogs and cat, people argue they're very different, but the word dog and the word cat, they're used in very similar ways, right? Like I love my pet cat, I love my pet dog. Dogs are pets, cats are pets. Now, if you look at the one below that, dog and puppy, so you would anticipate that to have a higher relationship with us. It's 0.86, because dogs and puppies are used in the same way as dogs and cat, but puppy is closer to dog. Dog and hot dog, just a fun one there. Pretty low similarity, thankfully, 0.33. Cool and awesome, pretty high similarity there is 0.76. So cool and awesome in whatever corpus, and this was actually from Wikipedia. In that corpus, in that text, cool and awesome were used more similarly than cool and cold. So the temperature cool and cold, which was 0.56. So still relatively high, but lower than the relationship between cool and awesome, 0.76. So back to the model. So instead of training the model on the existence of certain words based on the utterances or the examples that are provided, we train it on the meaning of the words, the embeddings. What this enables us to do is utilize the semantics. That instead of saying, "Hey, this word wasn't found here," so we can't make a prediction, or it's a 0 and 1. We can use the vector itself or the embedding to better understand. And I'll show you an example of that. So this is similar to the previous example with a bag of words. Now, both a bag of words and this example, these illustrations here, this is what I was talking about, oversimplification. This isn't really how it works totally, but it's been reduced to something that can be kind of explained in a more intuitive fashion. So if you think about it, before what we were looking at was like the vocabulary and whether or not the word existed. But now what we can look at is the semantic similarity by comparing the two words themselves and using those embeddings. So transfer money. And like I said, this is not exactly how it works, but if you consider transfer being transfer and money, that's 1 and 1. Transfer money, please, 1 and 1. Money transfer, same thing. Now, transfer human. This is something that the bag of words got correctly because of the lack of money and the existence of human. Human and money have a score of 0.26, so that's pretty low. So you would imagine that these two numbers here, the assistant would still say unknown. It's still the relationship between transfer human and transfer money is pretty low as far as the similarity goes. Now this is the one, transfer funds. The last one is the one that the bag of words model struggled on because of the word funds. In this case, funds and money have a relationship, a similarity of 0.72 according to these embeddings, which is pretty high. So then we can use this input 1 and 0.72 to be more confident that this is a transfer request. So the big difference here is instead of just using the existence of the word, like the bag of words approach, we can use the meaning of the word. And the meaning of the word of funds and the meaning of the word money, according to those embeddings, allows the assistant to understand, okay, these are similar things. I can make a transfer request based on that information. So those are the some of the approaches to intent classification. Some challenges with any approach. Vagueness. So if the user is quite vague on what they want, if they just say transfer, that can mean many things. It can mean that they want to transfer money, they want to transfer to a human, they want to transfer money to an outside account. Lots of different things that that transfer can be associated with. So some solutions there are to either ask the user to be more specific or give them some options on what can trigger transfer, like some more specific options. And long form text can be troublesome from the intent classification point of view because there can be many different intents embedded within a single request. In this case, a person's asking for help, transferring money, not sure how much money they have, so an account balance, and the routing number. So that can be problematic when you have so many different requests embedded within a single request. There are some solutions for that. What you can do is you can try to identify all the different intents within that utterance, split it out, but it still remains a challenge. So entity recognition. So those were some approaches for intent classification. Entity recognition is essentially, is there any important data in the user's request? Different entity types would be dates, numbers, locations, cuisine, things that are little pieces of information that make the request more detailed that the assistant can use to make a better experience. So in this example, these examples are from previously. You can see that it's about 200,000. 200,000 is a number entity, specifically money. And this user, even though they're asking for restaurants, they're asking specifically for sushi restaurants. So the sushi aspect of this that's the cuisine, that's an entity. So what the TripAdvisor bot can do is say, okay, they're asking me about restaurants. Instead of searching through all restaurants and providing that list to them, I can hone in on sushi because that's specifically what they're asking for to make for a better experience. Some approaches to entity recognition. This one's pretty straightforward. It's similar to the intent classification. It's a lookup. You create a list of entities and you check if the utterance contains any of those entities. So if I were to create a cuisine like sushi, barbecue, vegetarian, you can see that sushi is within that request, find sushi restaurants, and it would be recognized as an entity. I could use that information to further hone in on any type of action that the assistant needs to do. Now, some things aren't super easy to define. They're more open-ended. This is where you would want to use something like pattern matching. An example of something that would be open-ended would be phone numbers. So you're not going to create a list of millions and millions of phone numbers to be recognized. What you can do is you can use pattern matching, regular expressions to define a regular expression to match certain formats that you're looking for. So this regular expression here will match all of these different formats for phone number. You can do the same with social security number. Basically, some people do it with addresses. Addresses are a little bit more sophisticated. So it's difficult to really get a pattern match on that. But pattern matching is useful if you want something that's very specific on an open-ended entity type. So those were two rule-based. So rule-based would be lookup, pattern matching. Now, there's also the opportunity to create machine learning models for this. as well. And one of those approaches is called sequence tagging. So in order to create a model for sequence tagging, what you need to do is you need to give the model a list of utterances that contain the entity. And within that list of utterances, you need to tag what is an entity and what's not an entity. When the model sees an utterance, when the assistant sees an utterance, it'll predict word for word whether or not that a word is an entity, and it uses the surrounding context, the surrounding words. So we'll see how that works here. Simple example. So the top two, my phone number is 8675309. You can call me at 8675309. Thanks. Those are training examples. That's data that we feed the model. The O basically represents not an entity, and then phone is the phone entity. So for each, we code the model, hey, this is not an entity, and this is an entity, in this case, phone. When a user utterance comes in that we haven't seen before, like phone number is 8675309, hopefully the model can predict word for word what each word is. So ideally, you would get phone number is as all as not entities, and then 8675309 as the phone. And this is using the surrounding context. You can see like phone number is, those are common. Those are seen already in the train data. Phone number. You can imagine if you have a giant list of these training utterances, you could have a lot of variation. So the more data in this type of model is better. The model can use that context to help understand which word is an entity and which word is not. In addition to sequence tagging, what you can do is just something as simple as text classification. So it's the same idea. You create a list of utterances that include the entity to train. Instead of looking at the surrounding words, you really just focus on the word itself. So whereas in this particular model, all of those words are taken into consideration. It's looking at, when it sees the word phone in the training, it's also looking at the word before and after. It's looking around it. In this example, you're only really focusing on the word itself. And this would be an example of that. Say you have, you've given a model like a list of cuisines, sushi, barbecue, vegetarian, maybe some more. And a user says, find me a hamburger joint. So this model is not looking at the word. It's not trying to use the word, like when it looks at hamburger, it's only looking at the word hamburger. It's not looking at find me a, and it's not looking at joint. It's looking at only the word, none of the surrounding context. And because you've trained a model that already has words that are similar to hamburger, like sushi, barbecue, vegetarian, because of the embeddings, it knows that relationship, this is all food. It can understand that hamburger is a cuisine type. It sees that hamburger is similar to sushi, barbecue, and vegetarian, and makes that prediction. So the difference between these two is on the first one, sequence tagging, it uses the surrounding context to help it make a prediction. On this particular example, it's only looking at the word itself. And there can be pros and cons to each of those approaches. Some challenges in entity recognition: colloquialisms. So some people refer to entities in different ways. $50, send $50. $50 might not be used by everybody to denote a dollar amount. So there are definitely geographical colloquialisms, just regional, local, that need to be accounted for in order to really fully understand the entity. And there's also the issue of should something be an entity. In this example, the user asks, what are your current student loan refinance rates? So you can look at this two different ways. You can look at this as the intent is student loan refinance request, or you can look at it as this is a loan request with the entity student. So in the first example, it's an intent. It's, you're training specific utterances with student loan refinance. In the second example, you just have a general loan intent, but the entity here is student loan. So you use that information. So you can kind of guide and design it how you want to do it. There's, it's very opinionated, but that's one of the challenges, is deciding whether or not something should be an entity or not. The last core component of natural language understanding NLU from the assistant's perspective is dialogue. And there's two big pieces of dialogue, or two big aspects of dialogue that we should consider for the NLU. Has the user said anything previously that may affect the current interpretation of the request? And is there any additional information that needs to be gathered to complete the flow? What are the next steps, kind of thing? So here are two examples. In this example on the left, the assistant is asking if the user would like to start getting a rate quote. And the user says, sure, let's do it. And the agent responds, okay, great. So in this case, it's showing what the user is saying. The interpretation of what the user is saying depends on the previous interaction. So the agent or the assistant is asking, hey, you want to start a rate quote? The user says, sure, let's do it. And the assistant says, okay, great. Now, if the user just said, sure, let's do it out of nowhere, the assistant probably wouldn't understand what the user was saying, like as just alone, standalone, sure, let's do it, wouldn't understand it. So the fact that it's using the previous state of the assistant to understand it shows the dialogue aspect. The second example is gathering information. So the assistant knows that it needs to continue gathering information. So how much do you currently owe on all your student loans? And the user responds. So those are the two big aspects. It's the interpretation of the request based on previous states, or with previous states in consideration, as well as the gathering of additional information. So also going to go through a rule-based and ML-based approach for this. State machine is a rule-based approach. You can think of it as sort of like a decision tree or flow chart. It keeps track of what state the agent is in, or the assistant is in, and defines the rules based on that. So you can see here, this is an example of ordering flowers. You can go through that flow. If the user just says, I want a bouquet, it goes straight into the gathering more information about what kind of bouquet. If the user says hello, the assistant responds with, what would you like? What kind of bouquet would you like? But this is very defined. It's all outlined. It's decided upon. It's a decision tree. It's pre-planned. It's rule-based. This is something that's been created by somebody. So the assistant will follow this kind of line by line and not veer from it. This would be considered a rule-based approach. Another approach, which is more on the ML side, machine learning side of things, would be considered, is reinforcement learning. And essentially what this is instead of giving the assistant like a predefined flow to follow, it needs to follow this, you give it a set of states, possible states and actions, and you let it make those actions or perform actions at a given state and reward it accordingly based on how correct the action was. So in this case, the assistant is learning more so by trial and error, and it's open, it's interactive. There's no predefined flow or decision tree. It's, hey, here's the playground, go play in it. And so the assistant can learn by trial and error, getting rewarded for making the right decision, being punished technically or not getting rewarded for making it wrong, and understand and learn what it should be doing on its own through that interaction. So on one hand, you have the rule-based approach, the predefined decision tree or flow. On the other hand, you've got the ML approach, which is, hey, here's a set of things that you can do at certain points. Go ahead and have at it, and you'll be rewarded or punished accordingly. It's almost human-like in the nature of the learning. So here's a simple diagram that there's a state. The agent is at a certain state. In this case, or the assistant, it takes an action on an environment. So if there's an interaction, a conversation, something decides whether or not that was the right decision, provides the reward or lack of reward to the assistant, updates the state, and then this just continues on and on until a certain point. Some challenges with dialogue, when to use it, when not to. And what I mean by that is carryover, essentially and specifically. So this example is somebody's asking for their checking account balance, and the assistant responds, your checking account balance is. So in this case, the assistant knows that they just asked about their checking account. So it's kind of storing that. It's in that state, like they just recently asked about their checking account. And then the user recent transactions. And the assistant says recent transactions from checking account. So it specifically points out or filters to the recent transactions from the checking account, not recent transactions in general. Now, this can be, depending on what side you are, this is a good thing or a bad thing. Some people would argue that the UX, it shouldn't make the assumption that they're asking about the checking account specifically. And others would argue that it's a better experience because they just recently asked about the checking account, that it should give them recent transactions for checking account. So I don't think there's an answer, a correct answer to it. It really just depends on your perspective on the UX. But maybe over time, data will tell us, hey, this is preferred one way or another. But that is a challenge for dialogue, is understanding when to persist certain information across and through the conversation. So putting it all together here, this is just an example, and it kind of embeds all those intent classification, entity recognition, and dialogue into one screenshot. So you can see that the user asked student loan refinance rates. That's the intent. The assistant understands it, asks if they want to get started. They say sure, so some dialogue there. Continues on, deciding which action to take. Asks how much they have in student loans. They say about 200,000, so that 200,000 is the entity recognition. And then that continues the conversation forward. So this does a great job illustrating intent classification, entity recognition, and dialogue all in one conversation. So some closing thoughts. Rule-based and ML, they've got their pros and cons. There's not necessarily like the right answer. You shouldn't say that this one's always better than the other one. Rule-based is more controllable. ML is more scalable. You don't have to, you can use data, not, data-driven, not developer-driven. One size doesn't necessarily fit all. So I prefer a hybrid approach myself, using different technologies wherever they're needed. But if you only had to pick one, I would say pick ML. It's getting that good. And yeah, it's always improving. And it's a little bit, I think, more manageable. Newer is not always better, but it usually is. It really depends on your needs. So technology is always coming out, new technology, especially in the field of AI. Always some like flashy objects and some fun toys coming out. So it's hard not to chase some of that, but usually it's a good thing because the technology will improve everything. Upstream processes are also very important. So that's like, text processing, something like case normalization, spell correction. And it's awesome that the assistant creation in general, it's just becoming so much more accessible and more convenient because of open source libraries, free services across the board. So if you're interested, you can definitely get started pretty easily just through searching on the web. That's the end. There's just a few different ways to say that. I thought it was pretty funny because we were speaking about embeddings. So we're finished. It's over next time. Conclusion, closing time. So I know we don't have a ton of time for questions. Only a few minutes here. So if you do have questions, feel free to throw them in the chat. And if not, you can email me directly. I'll put that in the chat too. Jordan@Abe.ai. So if you have any questions about where to get started, how to build an assistant, feel free to send a message my way. And thank you for sticking around. Appreciate it. All right, signing off. Thanks, everybody.